this video briefly covers moment of inertia. So let's say that we have two different masses attached to a rod that has a fixed axis and is rotated. We could say that the system's kinetic energy was equal to the sum of the kinetic energy of each mass, which is just simply 1/2 mv squared. This kinetic energy equation might be a little difficult to work with since each mass has a different linear speed. But we do know that since they're attached to a rod, they're going to have the same angular speed. So let's define the radius as the distance from the axis of rotation to each mass. We can say that the velocity of the first mass, m1, is going to simply equal that radius times the angular speed. And the same thing goes for the velocity of the second mass. We can then use these relationships to simplify our kinetic energy equation. So we can substitute in these velocities, and we notice that we have this quantity of the mass times the radius squared. And this quantity is called the moment of inertia. And the rotational kinetic energy can then be redefined as 1/2 times the moment of inertia times the angular velocity squared. Important equation. So we probably noticed that the moment of inertia is going to depend on an object's axis of rotation. So take, for example, we have these two masses connected by a rigid rod. So let's find the moment of inertia if we decide to fix the left side of this rod. So fix where m1 is. That means that m1 is not going to have a velocity, or the distance to m1 is going to be 0. So we find that our moment of inertia is just simply m2 times r squared. Now let's find the moment of inertia if we decide to fix the right side of the object. So then the distance to m1 is going to be negative r, and the distance to m2 to the right side is going to just equal 0. So we get the moment of inertia is equal to m1 r squared. Alrighty, now let's look if we decide to fix the center. So each mass is going to be a distance of r divided by 2 away from the axis of rotation. And when we do this all out, we see that the moment of inertia for the center is going to equal the sum of the masses times the radius squared divided by 4. So let's do another quick example, finding the moment of inertia about the origin of these three masses that are scattered in 2 dimensions. So we're going to find our r values using the Pythagorean theorem. So the distance from the origin to the 1 kilogram mass is 2.24 meters. The distance from the origin to the 2 kilogram mass is 2.83 meters. And the distance from the origin to the 4 kilogram mass is 4.12 meters. Next, we can plug these values into our equation for moment of inertia. And when we plug and chug, we see that the moment of inertia is 8.89 kilogram meters squared. Now let's find the moment of inertia around the point 2, 2. The distances to the two other masses are again found with the Pythagorean theorem. And we're going to sum these masses times their distances squared. And notice how the distance to the 2 kilogram mass is 0 since we're choosing this to be our fixed axis of rotation. We then find that this moment of inertia is equal to 77.13 kilogram meters squared. So there are a lot of general formulas for moment of inertia for different kinds of objects. For a hoop with an axis about the center, we say that the moment of inertia is equal to the mass times the radius squared. For a solid disk with the axis around the center, we say the moment of inertia is 1/2 times the mass times the radius squared. For a stick with the axis at the center, we're going to say that the moment of inertia is 1/12 times the mass times the length of the stick squared. For a stick with the axis at the end, we're going to say that the moment of inertia is equal to 1/3 times the mass times the length of the stick squared. And for a solid sphere with an axis at the center, we're going to say that its moment of inertia is 2/5 times the mass times the radius squared.